Howdy, howdy. Have you ever wondered how a Commodore 64 keyboard works? Probably not, but if you're watching this, maybe you have wondered how it works. And today I'm going to get into the internals about how the wiring is done inside a Commodore 64, how that keys are processed, what a keyboard matrix is, and how that works, as well as some flaws in the design, or at least some limitations in the design that in how Commodore approached building a keyboard. But this keyboard is super simple, and I think it's actually really interesting to learn from. I learned a lot by doing this project, and so I hope you will too. So why did I do this to begin with? Well, as I mentioned in some previous videos, I'm building a breadboard computer, and I wanted a really cool way to interface with that computer. I have a bunch of old Commodore 64 stuff lying around, including some old keyboards, and I wanted to put one of those to good use and also learn even more about how the Commodore works because it's kind of basically my favorite computer, I think, at this point. And so it was a good opportunity for me to learn, to explore a little bit, and then to share it with all of y'all, and hopefully you find it interesting as well as I did. It's actually quite simple, pretty straightforward how it works, but there are some flaws with it, some limitations in the design that we'll talk through in this video. All right, let me show the keyboard in action. You can see I can type on the keyboard, scrolls. Oops, got a typo there, and I think I saw a typo on the board. So type. Works a lot like the original C64 keyboard, so I can insert spaces in the middle. Hit return, unknown command. I've built a basic machine code monitor. So you can see, I can see what's at memory 1000. Let's see what's at 1008. By just going next, I can go, oops, I can go back to the previous memory location, see what's at 1000. I can change this to B224, and you can see it updated. I actually have history here, so you can go back and see 18 lines of history and see every thing that you typed before. So kind of fairly functional interface here. Everything's reasonably zippy. It gets a little slow when I'm backspacing because of the way I do the updates in that case. But so it's not perfect, but it works pretty well. Okay, so how does this actually work? So inside of the Commodore 64, there's a 6526 chip. They call it the CIA, which is basically an input-output virtual interface adapter thingy. And it's got two ports on it, each with 8 bits. And these are wired into the keyboard directly. And so on the motherboard, actually I have an old motherboard. So labeled CN1 here, there's a set of pins right here, and the keyboard connector connects directly into those pins. But basically, just a set of pins, and these are wired straight into, as you can see from the schematic, port A and port B on that 6526. The way this actually works, I'll zoom out a little bit here, and you can see that there's a matrix. And so what's called a column, so each column on the 6526 chip tied into a specific bit on a specific port. So let's say PA0 is column 0, and you can see that all of these keys in a matrix are on that column. So delete, return, cursor right, F7, F1, F3, F5, cursor down are all wired directly into this column 0. Similarly, column 1, you have 3, W, etc. And so there are 64 keys. Actually, there's 65 on the Commodore 64 keyboard. I'll get into the restore key later. But there's basically 64 normal keys on the keyboard, and they're organized into a series of 8 columns, columns 0 through 7, and 8 rows, rows 0 through 7. And so this delete key, let's say, is on column 0, row 0. So delete 3, 5, 7, 9, plus, pound, and 1 all share the same row, and delete, return, cursor right, F7, F1, F3, F5, and cursor down all share the same column. Okay, so how does the C64 actually know what key is being pressed at a given time? The way that works is actually relatively simple, but it's fairly CPU intensive. So 60 times a second, it'll do a scan, and it will scan each of these columns one after the other after the other. And the way it scans is, by default, it's outputting ones on every column except the one it's scanning. So, 1/60th of a second passes, it now does another scan. It will set column 1 to 0 and everything else to 1, and then right after it does that, it will set column 1 to 0 and everything else to 1, then it'll set column 2 to 0 and everything else then 1 to 1. This line right here from this A into row 2 is basically just floating. There is no, like, until this switch is made, it's just a floating input into this 6526 port. Now I believe there's a pull-up resistor built in, so that's why this reads a 1. Once you press this A key down, and if this is 0, then this line output becomes 0. And so then we know when that scan is done, if we're scanning column 1 and we see this row 2 right here that this A is on go to 0, then we know that that key is being pressed. So it's relatively straightforward, very quite simple. It's just literally a circuit going all these keys connected on a single column, and then all these keys connected on a single row. And so then you might wonder, how do I actually know if, let's say, this row 2 here goes to 0? We know something on that row has been pressed. How do we know whether it's the A, the D, the G, the J, etc.? Well, we know that because we're actually actively scanning this column. So we're scanning column 1, and we know because column 1 is 0 and row 2 is 0 that the A key was pressed. So there are some flaws with this approach. One of those flaws is that it's very CPU intensive. And so as I mentioned, every 60th of a second, it has to scan each of these columns, see which keys are being pressed, and so there's some loading of the accumulator, then there's a lot of comparisons, and it's just like a super expensive thing that on the Commodore 64 is done directly on the CPU. On the computer that I built, all of that work is done inside of the Arduino, and so I actually have an interrupt wired up between the Arduino and the VIA chip on my computer, and so I will do the scan very frequently on the Arduino, but the CPU on my computer only really responds to that interrupt and then does its work. So that's one of the flaws. And then another flaw is really that there are situations that you can get in where the computer will get confused as to what key is actually being pressed. So let's say, for example, we're scanning line 0 here, and let's say while we're doing that, keys K, S, and A are being pressed. And so it's quite obvious when this goes to 0 and K is being pressed, then K's row 6 or row 5 over here is going to go to 0, and the computer is going to know that K is being pressed, right? Because it's scanning this column here, and this row goes to 0, and so it knows that key is being pressed. However, in this specific situation, the computer is actually going to also think that J is being pressed, even though it's not. And the reason for that is that this line is going to go to 0, but because A down here is being pressed, this circuit is going to get closed, and then row 2 down here is going to go to 0 as well. Because these all share the same row, the same wiring, closing any of the keys on this circuit, the computer cannot tell which of these keys was actually being pressed except by looking at the column, as I mentioned before. But because this column actually went to 0, because we're actually scanning it, and this row is 0, the computer thinks that the J is being pressed even though it's not. And so I'm on a live C64 right now, as you can see on the screen, and I'm going to press the A, S, and J keys at the same time. And as you can see, I'm pressing A, S, and J. However, K is making an appearance in there due to the reason I showed earlier. And so, as you can see, it's not just a flaw in the computer that I built, but just a general inherent flaw in the design of the Commodore 64 keyboard. I mean, I guess you can call it a flaw, or you can just call it a constraint, a design constraint, because this is actually super simple, and I think it's pretty cool how it works. So, there you go. Okay, so I'm not going to go too deeply into the rest of the wiring for this keyboard, but the pin 1 basically goes to ground. Pin 4 is the 5 volts, but I don't think that actually runs anywhere inside the keyboard. 2 was set up for future use, but doesn't actually do anything. And then the restore key, and I'm not going to go into details about this. I haven't actually really researched what it does. But you can look online. But basically, it's wired directly into a restore line on the computer. So it's not handled via the same general matrix and the same scanning mechanism as the rest of the keyboard is. Okay, so let's see how this is actually wired up to my breadboard. As you can see, the Commodore 64 has a whole bunch of wires coming off, and I have those heading into basically an Arduino Nano. So these last 8 are the port A inputs, and the 8 before that are the outputs. And so you can see I have let's aim the camera, a shift register, 2 shift registers on my computer. So one of them here is feeding the input onto the keyboard. One of them is feeding a via 6522 chip that I have on the computer. And then I have the outputs from the keyboard heading into some of the digital ports on the Arduino. What ends up happening when you type a key is that these are scanning. So if I clear my screen a little bit, so it appears to be working. I must have unplugged. Oh, look at that. That came unplugged. There we go. Now does backspace work? Yes, now backspace works. Had a moment of panic there. Okay, so the way this works is 60 times a second it will scan each of the columns, and so those are output via this shift register here. On the first scan, all of these are outputting a 1 except for one column, and then when I am pressing a switch, like let's say S, so S is being typed up there, on that scan, one of these lines goes to 0, the column that S is on, and then S, a connection is made through that switch, which is now closed, from the shift register through the S switch over to one of the lines on the Arduino. And so right now these are pull-up resistors here, and they're basically just floating until, well, they're pulled up, but they would be floating if these were not connected to a pull-up inside of the Arduino. And there is no then physical connection between the output here and the input here. But when I press the S, that circuit is closed, and so this is driving a 0 through here, which then results in a 0 on this end, and we know that I was scanning the column that the S is on, and because it goes to 0 on the output, then we know that, or the input of the Arduino, we know that it was the S key that was pressed. Okay, so I'm going to walk through the Arduino code. I'm just going to do a very brief overview of the code. I'm not going to go into tons and tons of detail about it, but just kind of give some indication of how it works. So at the top of the code, and all this is in GitHub, so at the top of the code you can see just some hint at how all of it is wired together. I have this map of ASCII characters associated with the rows and columns from the for the Commodore 64 keyboard, but I chose not to actually send these ASCII characters to my breadboard computer and instead use PS2 scan codes for that, partially because on the breadboard side I wanted to be able to someday potentially use both this Commodore 64 keyboard and switch over to a PS2 keyboard if I so desired. Note that there are some Commodore 64 keys that don't really have equivalents in PS2, and because I am using a subset of PS2, I've kind of abused that, and I'm using some special PS2 scan codes rather than what they actually were intended for. So it's a bit of a hack, but I do. And so this is a map of PS2 keyboards scan codes based on the same rows and columns that this is based on, but this is the actual scan codes from the PS2 spec that will be sent when particular keys are pressed. Not going to go into tons of detail in the code, but I did want to show how the scanning is done. And so a very basic loop, and I basically scan each column. And I'll show you in the output what that actually looks like in a moment. And then for each column, I basically see whether I do a read for the rows and see which keys are pressed based on which of those return 0. So I'm going to now connect to the Arduino so you can see the output of this on the serial monitor. And so as you can see, I'm scanning row by row by row. So this right here represents the column. So first I'm scanning column 0, then 1, then 2, then 3, then 4, then 5, then 6, then 7. I put a 2-second delay in just for the purpose of this demo, so you can see. And then these are the rows. And if it's a 1, that means that key is not being pressed. If it's a 0, that means the key is being pressed. And then I've printed on the side here the Commodore 64 keys associated with the rows. And so the way to read this would be if this is a 0, well, I'll jump down here since it's scrolling. If this is a 0, right here, the second one, and then let's say the second bit here is set, that would mean the E is being pressed. And so I'm going to now press the A key on the Commodore 64 keyboard, so when it scans row 1, you should see this A light up. Okay, so I'm officially holding down A, but because I have the 2-second delay, it's going to take a moment. You'll notice it's all 1s, except all of a sudden that the A key went to a 0. So you can see that the A here went to a 0. So I'm scanning column 1 and row 0, 1, 2 went to 0. So then we know that A key is being pressed. Okay, and now I'm going to press A and S at the same time, and you will see when it comes back around to that the key associated with S, so this bit right here and this bit right here are going to go 0 on the next scan right here. Okay, so both of those are 0, so now S and A are being pressed at the same time. And now, as I said earlier, there are some flaws with how this works, and I'm going to show that right now. So I'm going to press the A, the S, and the K key at the same time. And so you see on that scan for column 1, A and S lit up. And then when we get to column 4, you'll note, and I just released, when we get to column 4, let me unplug so I can stop the scrolling. When we get to column 4 here, you see that both the K key and the J key are reading 0s, even though I was not pressing both of them. And again, that's for the reason I described earlier, and you can see that in action here. And so this again is one of the constraints of the Commodore 64 keyboard by this design. So this code is out on GitHub. Now, one more thing I want to cover. As I mentioned, this is a very CPU intensive process, and so on the original Commodore 64, this is all done on the CPU, and there's no interrupt. It's just doing a scan, to my understanding. Instead of that, I've actually wired up an interrupt, and so that is on my Arduino. Where did I actually mark that? IRQ, so A0 on my Arduino. I use that to trigger an interrupt on my breadboard computer via the VIA chip on the computer, which then interrupts the processor, basically, and so we know that a key was pressed. And you can see the assembly code for that in the repo also. And so basically when that interrupt occurs, it's reading the port on the VIA chip to know what key is actually there. I actually also implemented a repeat. So basically, I'm scanning every 15,880 microseconds to get to roughly 60 hertz, so 60 times a second. In between scan codes, I wait 40 milliseconds. I think microseconds. That's how long the line is held inactive between scan codes, and so I think the PS2 says do this between 20 and 50, so I just set it to 40. And then I determine that we're in a repeat after 60 scans. So if a key is being pressed for 60 scans, basically a second, then we're in repeat mode, and I will send the key again. And then the key, once the key is released, it follows the PS2 spec. We'll send a release signal and then followed by the key again. All right, I think that is all I need to cover on this stuff.